In our previous lesson, we learned how to solve quadratic equations, but sometimes it's helpful to be able to quickly figure out if an equation is solvable at all, or if there's one solution or two solutions. So that's what we're going to do in the lesson. So by the end of this lesson, we should be able to determine the number of solutions of a quadratic equation by using something called the discriminant. So to help to illustrate this, let's go to the graphs of a quadratic function. So there's three options. Let's take a look at our first option. Our first option is that our our function could have two distinct roots. So graphically, this is going to look like two x-intercepts. Algebraically, this would mean that if we were to take this quadratic equation, set it equal to 0, we would get two solutions. Another option is if we were to graph a parabola, it could look something like this, where there's only one x-intercept or one root. Again, that's what it would look like graphically. Algebraically, if we took this equation, set it equal to 0, we would only get one solution, or the same solution twice. That's the reason why we say two equal roots is, let's say that x-intercept is 2, then the equation would look something like this, all squared, which is x minus 2 times x minus 2, which means the two x-intercepts are equal and they're both 2. So that's why we say two equal roots. And our last option is if our quadratic has no solution at all. So maybe it looks something like this, in which case it has no x-intercepts, so no roots. And if we were to take the equation of this quadratic and set it equal to 0, we would get exactly 0 solutions, because the function is never going to equal 0 because it doesn't have any x-intercepts. So we know if we wanted to solve a quadratic equation, we could always use the quadratic formula to help us. So quadratic formula is always going to work. And it can also help us to determine the nature of roots without solving for them. And we're going to go through that next. But just so that we're all on the same page, when we say the nature of roots, we mean whether or not the equation has real roots, and if there are real roots, whether they're different or equal. So that really means, is there one solution, is there two solutions, or is there no solutions? So we're given three equations here, and they're all set to equal 0, so the hard work is already done for us. What I'd like you to do is quickly determine the solutions, or maybe there's no solutions, to each of these quadratic equations using the quadratic formula, and then rejoin the video, and we're going to go from there. So once you've come up with your solutions, in the first example A, you should come up with two solutions. Second example, you should come up with one solution or two equal solutions. And our last example doesn't have any solutions at all. So we're just going to add in these notes. Number of solutions for the first one was 2. Number of solutions here. And by solutions, I mean unique solutions, so different ones. So 2 different ones for A, 1 unique one for B, and 0 solutions for C. So we want to find a faster way to be able to determine whether an equation is solvable at all. So that's to say, is there a solution at all? And is there one solution, or is there two solutions? So that's going to come from whatever is underneath the square root sign. So we can understand that if there's a negative under the square root sign, a negative number, we know we cannot find the square root of it. So automatically, if whatever's under the square root is less than 0, there's going to be no solutions. If it's exactly equal to 0, well, in the next step, we're adding and subtracting 0 to whatever our first number is here. And if you add 0 or subtract 0, you're going to get the exact same number. So if whatever is under the square root is equal to 0, then we're only going to get one solution. And lastly, if whatever is under the square root is a positive number, well, we know we're going to get two different options. So in this example, we had -1 plus 5 divided by 2 and -1 minus 5 divided by 2. So in summary, if what is underneath the square root, and that is called the discriminant. So if the discriminant is negative, then there's going to be no solutions. If it's equal to 0, there'll be one solution, and if it's positive, there'll be two solutions. So our conclusions from the previous page are all summarized here. So I was using the word discriminant, and here it is again. So the discriminant is just referring to what is under that square root sign, which is b squared minus 4ac. So if that discriminant is greater than 0, then business as usual, we have two different real roots. If it's equal to 0, that's when we're only going to get one unique root or two equal real roots. And the last is if our solution is less than 0, we're not going to have any solutions at all. So in the next example, we're asked to determine the number of solutions to each quadratic equation. So we're not going to find the exact solutions, we're just going to determine the number and the nature of them. So are there one, are there two, is there none? All right, so we're given a y value, f at x equals -5, so we're going to plug this guy in to start. So we have -5 is equal to 2x squared minus 3x minus 10. So graphically, what we're actually being asked to do right now is to check if there's a point of intersection between these two. We're setting them equal to each other. Another way to think about it is we're subbing in -5 in for f at x, and we're asking, can this function ever equal -5? Maybe it's entirely on top of it or entirely below it. We don't know. So to solve this thing, or to check if there's any solutions, we're again going to bring our -5 onto the other side so that we have our equation now set to 0. So we have 2x squared minus 3x, and then we're going to have minus 5. I got that because I took -10 plus 5, and it's going to give us -5. So if I were to graph this, I would be able to tell the number of solutions just from that graph. So if I were to graph this equation right here, it would let me know, do these two equations intersect? Can this parabola equal -5 at any point? Algebraically, let's just check the discriminant. So the discriminant, of course, is going to be whatever's underneath that square root sign. So it's b squared minus 4ac. And we're going to plug everything in. So our b is -3 all squared minus 4. A is 2, C is -5, and we're going to get 49. So that means that in our quadratic equation, we're going to have -b plus or minus the square root of 49. And we know that we can find the square root of 49, so this is going to give us two real solutions. And not only real, they're going to be two distinct. So two distinct or different solutions. So we're going to do the same thing for this guy here. We're given a new equation. We have a new f at x. So we're subbing in our f at x is equal to -3 into this equation. We're checking, do these two intersect at all? Can this function equal -3? We're not sure, so use the discriminant to check. But first, sub in your -3 into our equations, let it equal 0, and then go ahead and use the discriminant. So try that on your own. Come back to check your answer. So if you're checking back now, you should have gotten this equation. Our A, our B, and our C are here. Throw it into our equation for our discriminant, and you should get the discriminant is equal to 0, which means that we have that second case that we worked on the first page, where we're actually going to get only one unique solution. Another way to think of it is that we're going to have two equal solutions. Both of these are correct. So yes, these two functions can equal to each other, but it must just hit -3 and bounce back, which means that there's only going to be one point of intersection. And now let's do the same for our final example. Try it on your own, come back and check in. Alright, so when you set the equation equal to 0, you're going to get a discriminant of -39, which means if we were to throw this under the square root sign in the quadratic formula, we wouldn't get a solution at all. So this means that these two functions don't intersect at all, so this function can never equal -8. So therefore, there are no real solutions to this quadratic equation. So as I said, we can think about this as the point of intersection of these two functions. We can think about it as, can this function ever equal -8? Or when we bring these two equations together and set it equal to 0, another way to look at that is, does this equation have any x-intercepts? And that answer is no. So that's three different ways to look at the exact same problem. So now let's take a look at some application and thinking problems. So it says determine the value of k so that the quadratic function, blah, 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 here it is, has only one x-intercept. So we got to break this down. The key is that we were told it's that we're looking for an x-intercept and it has only one. So an x-intercept implies that we have to sub in f at x is equal to 0, because we know if we're trying to solve for the x-intercept, we know y is equal to 0. So let's start with that first. So we're going to sum f at x equals 0. So we have 0 is going to equal x squared minus kx plus 3. And now we're ready to use the second piece of information we were given, which is that it has only one x-intercept, which means that this equation here has to have only one unique solution. So only one unique solution or two equal solutions. So we know that we can tell that just from the discriminant. So even though this whole lesson is on discriminant, remember that math is just a series of tools that we can use to solve problems. So we have to be able to figure out, when do I need to use the discriminant? Well, this is a question that it would be helpful in, because it doesn't ask us to actually solve for the x-intercept. That would mean we need the quadratic formula. This just tells us the clue that there's only one solution to this. So we know that if there's only one solution, then the discriminant b squared minus 4ac has to equal 0. So let's go with it and just fill in our b, fill in our a, fill in our c, and let's see what happens as we go through. So we know our b value is just negative k. So instead of b, I'm going to write negative k all squared. So here's our a value. Our a value is 1. Here's our b value, and here's our c value, just to make it clear. Okay, so we have b squared, which is negative k squared, minus 4. Our a value is 1, and our c value is 3, and that all has to equal 0. So we have one equation, and we have one unknown, which means that we can solve for this, and our unknown value is k. So negative k squared, negative times a negative makes positive, k times k is going to be k squared. So we have k squared k squared minus 4 times 1 times 3 is going to be negative 12 is equal to 0. Keep on solving this. We have k squared is equal to 12. And keep on going. If we take the square root of both sides, we are going to get that k is equal to, don't forget your plus or minus sign. So we create a square root. So k is equal to plus or minus the square root of 12. And we know from our previous lessons on radicals, we know how to simplify this guy. We know that there's a perfect square root in there, which is 4. So let's break this up into k is equal to plus or minus the square root of 4 times 3. We're going to simplify that square root of 4 to 2. So we know k is equal to plus or minus 2 root 3, and there is our final solution. So therefore, in order for this equation here to have exactly one solution, our k value can equal 2 root 3, or k can equal negative 2 root 3. So for our last example, we have a business example. It says a market researcher predicted that the profit function for the first year of a new business would be this here. So we have profit is equal to this quadratic formula, or quadratic equation, where x is based on the number of items produced in thousands, and profit is also in thousands, therefore. So would it be possible for the business to break even in its first year? So we have to figure out, what does break even mean? So break even means that profit is equal to 0. So from a business standpoint, that means that all of your revenue and your sales that you bring in is exactly equal to the cost. So it's very difficult to be profitable in the first or even first few years of business, and all business owners are trying to just at least break even for those first few years, just so that they can at least cover their cost. So really this question's asking, is the profit allowed to equal 0? So we're given this equation here, p at x is equal to negative 0.3 x squared plus 3x minus 15. And we have to check, can p at x equal 0? We don't know. So sub it in and check. So if we set p at x equals 0, and we have our equation on the other side, does this have a solution? So graphically, if it did have a solution, our profit function would maybe look something like this, where we have two x-intercepts here. This is our profit. Here's our number of items sold in thousands. So this company would break even. As we can see here, would be the break-even points. Not only would it break even, but it would be very profitable. Another option, if it doesn't break even, it would look something like this. So again, here's our profit, here's our x. Maybe the problem exists entirely underneath the x-axis, in which case there's no break-even points. Not only are there no break-even points, at no point is this company going to be profitable in its first year because all of our profit is negative. A third and final option, I'll just draw it on the same graph, is that it comes up, hits the x-axis only one time. That would give us just one solution. So at only one point, at selling only one certain amount of goods, would it break even. The rest of the time it would just be having a negative profit, so its cost would be more than its revenue. So let's take a look at which case this is. Is it case 1, is it case 2, or is it case 3? So we've subbed in our 0 and we're checking, is it this case, is it this case, or is it this case where it can't equal 0 at all? So because it doesn't ask us what number of items do they need to produce to be profitable, what's their maximum profit, that's not what it's asking. It's just asking, is it possible? So why would we solve this when it would be so much faster to check if it was possible just by using the discriminant? So b squared minus 4ac. Can this equation actually equal 0? Let's check. So throw in for b, we have our 3 squared minus 4, our a is negative 0.3, and our c is negative 15. And we're going to get negative 9. So we know that that means in our quadratic formula, we'd have a negative 9 under that square root, and it would not be possible. So therefore, there are no solutions. No solutions. What does this actually mean for the question, though? This means that there's no possible way for this profit function to equal 0, which means that it's not this case here. Can't be this case. It's also not this red case here because there it equals 0. It has to be this case right here where the profit function exists entirely within negative profit. So it's never going to touch that x-axis at all. So therefore, this company is not going to break even in its first year.